Typing a complex function by hand takes time. Generating that same function with a large language model takes seconds. Most software engineers operate on a straightforward assumption. If an AI writes code in 3 seconds instead of 3 hours, the total energy expenditure must drop. But this bar chart comparing average carbon footprints proves the exact opposite. Data from a controlled experiment at King's College London reveals that the LLM-assisted approach dwarfs the manual baseline, generating a carbon footprint 32.7 times higher. Offloading human labor to remote data centers saves time. It does not save energy. To see exactly where that energy goes, we have to calculate the true environmental footprint of a single coding task from end to end. We will build this mathematical model from first principles, starting with the strict power states of a local laptop. Then, we will scale that equation up to the massive cooling infrastructure required by the cloud servers running models like GPT-4. Optimizing those data centers reveals a thermodynamic trap, forcing a direct trade-off between carbon emissions and resource depletion. Solving the sustainability of AI requires looking past the software layer and confronting the physical limits of hardware and natural resources. We begin in the local development environment, constrained by the isolated hardware of a single laptop. This equation defines a human's total energy consumption as the sum of 3 variables: coding energy, debugging energy, and testing energy. Local runtime power is strictly capped by the processor's thermal design power and the active RAM usage. Looking at this continuous line graph tracking power over time, a standard coding laptop pulls roughly a steady 4 watts during active use. Developers spend roughly 42% of their time debugging, but only a fraction of that time is spent actively compiling and running code. The CPU remains largely idle. Manual coding is a slow, time-intensive process, but its energy ceiling is structurally capped at a microscopic level. Shifting to the LLM-assisted workflow moves the computational load across the cloud. This new equation maps the LLM total energy. It consists of query energy consumption, the estimated time to add missing functionalities, and the estimated time for human insight. Breaking down the query energy consumption, the base inference cost for a single prompt sits at 0.0022 kilowatt-hours. Factoring in the amortized training cost of the model adds 0.0088 kilowatt-hours, bringing the total baseline energy cost per prompt to 0.011. That calculation assumes the AI generates a perfect solution on the first try, but generated code routinely fails test cases. This flowchart maps the standard developer reaction. Feed the error trace back into the LLM and force it into an iterative loop of reprompting, repeating up to 5 times. After multiple failures, the LLM hits a logic wall. The loop breaks, forcing the human developer to intervene and supply insight manually. Even after diagnosing the issue, the human must still spend local laptop time writing the missing functionalities themselves. An LLM query is rarely a one-off energy cost. It often triggers a compounding loop of high-energy cloud queries that still terminate in manual human labor. How does this workflow scale when the task requirements move from simple scripts to complex logic? This scatter plot charts the empirical correlation between task complexity on the x-axis and the resulting carbon footprint difference on the y-axis. On simple tasks, high zero-shot success rates mean the LLM loop remains short. The data clusters tightly in the lower left, maintaining relative efficiency. On complex tasks, the LLM consistently fails edge cases, triggering maximum iterative loops. The data charts a steep failure cascade into the upper right quadrant. Complex tasks carry a double penalty. Developers pay the massive cloud cost for multiple query failures and still pay the manual debugging cost locally. LLM efficiency scales inversely with logical complexity. The harder the programming problem, the more punitive the carbon tax becomes. Every query in that loop requires physical infrastructure to process. But standard energy models contain a critical vulnerability. They rely on a flat, average grid carbon intensity to calculate emissions, ignoring the mechanics of the facilities themselves. This architectural schematic defines power usage effectiveness, or PUE. It measures how much overhead power a facility uses to run its cooling systems. To lower PUE and reduce their carbon footprint, data centers install highly efficient water-cooled chillers or massive cooling towers. But this introduces a countermetric, water usage effectiveness, which measures the liters of water consumed per kilowatt-hour of IT energy. Building data centers in water-scarce regions or under strict utility regulations forces facilities to abandon water cooling entirely. The alternative is relying on air-cooled chillers. These use zero water, achieving a perfect WUE, but they require massive amounts of electricity to run giant fans. That massive electricity demand drives the PUE back up, subsequently spiking the overall carbon footprint of every LLM query hitting that server. Software engineers can optimize their code all they want, but data centers are locked in a zero-sum thermodynamic trade-off between carbon emissions and aquifer depletion. Given the uncompromising reality of data center physics, we have to reevaluate that initial 32.7x carbon multiplier. This three-axis graph maps task complexity against carbon footprint and water usage. Manual coding yields a flat trajectory hugging the floor. Conversely, the LLM approach reveals an exponential curve shooting upwards and outwards on all three metrics as difficulty scales. The exponential cost of AI is not a software bug that will be patched out. It is a fundamental hardware reality tied directly to offloading cognitive work to megawatt-scale infrastructure. This reality requires a shift in the daily workflow and decision-making matrix of a modern software engineer. Green coding means treating AI tools as targeted, strategic deployments rather than blanket defaults. LLMs should be deployed exclusively for low-complexity boiler generation where zero-shot success is highly probable. Engineers must manually execute complex, logic-heavy requirements and edge cases to avoid triggering the compounding loop of cloud failures. For complex tasks, manual coding is functionally reliable, and it remains the only thermodynamically sustainable choice.